My guest today is Professor Tim Maudlin, who's professor of philosophy at NYU. His research interests include foundations of physics, metaphysics, logic, and philosophy of science. Welcome, Tim.
Hi, glad to be here.
Yeah, thanks for doing this so late in Croatia. As I mentioned, Tim, I don't have a deep background in physics, but I'm very interested in these topics. So I go to sleep every night imagining I'm falling into a black hole, that is space and time together there. And the experience has been very satisfying, actually. I don't know if it actually works. Um, but you have been thinking about sort of the foundations of physics. So I used to be an engineer, when we think about a building or a bridge or something, we sort of think about the foundations first.
Yeah,
And then, foundations are quite important because the foundations don't work. The thing is sort of
I
and
just got
going
that.
to, yeah,
That's a
he can join as well. Yeah.
hey, buddy.
And everything doesn't work. So, um, if I understand you correctly, physics has been going in a lot of different directions. I mean, a lot of different theories, a lot of different ideas,
hmm
but we don't really have a very fundamental understanding of what's driving it, right? Is that fair?
That is fair. I mean, I think when you talk about building a building, um, it's a slightly different situation. So the what we call the foundations of physics involve physical theory done at the most fundamental level that we have. Um, However, the rest of physics certainly does not rest upon those foundations in the sense of you make use of them for doing the rest of physics. I mean, for example, the best theory we have, foundational theory of matter, is quantum theory. We can kind of solve the hydrogen atom and
Yeah.
maybe the helium atom, but once you get beyond that, we can write down the equations, but even the best computers can't solve them. So it's not as if people are depending on that in a very deep way. There's
Hmm.
a lot of physics that's done um, at a kind of middle scale or mesoscale where they have their own principles. We think those principles themselves ultimately rest on
Hmm.
these foundational principles, but those parts of physics and of course biology and chemistry and so on can all go on perfectly well without worrying too much about what's going on the next three levels down.
Yeah.
Often this is called, in physics itself, this is often high energy physics. So the sorts of experiments they're doing at CERN with very, very powerful accelerators smashing individual atoms together or electrons and looking at tracks, things like that. At another level, the basic foundational question of the nature of space time is in general relativity. So it's not as if the rest of physics at a practical level
Hmm.
rests on the foundations. We just
Yes.
think on a theoretical level it does.
Right.
Um, and unfortunately, I mean, in a way, it's a very good thing because the conceptual situation at the foundational level is really quite a mess. And there's no agreement at all about what's going on. So if the rest of physics was waiting for that to be cleared up,
Yeah.
physics couldn't go on, or chemistry or biology.
So let me ask you this. So um, the direction that we are heading, and that is to say, we sort of have, general theory of relativity, quantum mechanics. We sort of understand some aspects for both of them. Um, the direction we are heading to the foundation, is that a direction that is going to be successful? In other words, there's just too much noise. So it's almost like we figured out the roof of the building, and there's a two color. There's a solar panels on one side, and some other thing on the other side, and that's fine. I mean, that's awesome. But can we ever get to the foundations in that
Well,
direction?
I see no reason why we can't. Unfortunately, for strange historical reasons, um, when quantum mechanics was developed in more or less its modern form in the mid-20s, and Niels Bohr and the Copenhagen people were involved, and Heisenberg, there was a fairly self-conscious move not to discuss the foundations, or to say, don't expect too much about being able to understand this theory. That eventually morphed into a slightly different attitude, which is called shut up and calculate, which basically says, okay, here are some equations, and here are some rules of thumb about how to use them, and you can grind some probabilistic predictions out of them. Just grind the probabilistic predictions out, and don't think about what it all means. So although people like Einstein and Schrödinger and John Bell, who we'll be talking about, were always very, very interested in these foundational questions, they really got pushed to the side, and physics students were actively discouraged from thinking about these questions. So I have no reason to think we can't make progress. I do have good reason to think that not that much effort has been put into doing work in this area, and that's more or less why I'm trying to promote it.
Yeah. So from an engineering perspective, Tim, I can understand Newtonian mechanics. It seems like, well articulated and well understood. We can now, we've talked a little bit about education toward the back end. We can now train computers to do all of Newtonian mechanics. So we don't need, well, let me make a statement. I don't know if you agree with it. You don't need civil structural engineers, mechanical engineers, electrical engineers anymore, because computers are fantastic to do all of that stuff. So that's a well sort of designed, articulated problem. And then Einstein comes along and creates some trouble in some sense. But we get a better understanding of gravity, right, from Einstein. And his concept of gravity was sort of a foreign concept, right, for an engineer in many ways.
And that's absolutely true. But it's an interesting situation. I mean, the situation you've articulated is exactly correct. But now let me just point out something that we all know is right. Newtonian mechanics is wrong. Right? It's just false. Yes. We know it's false in the main application where it worked, which was gravitational theory, because general relativity provides corrections, and those corrections turn out to be right, just empirically right. So we know Newton was wrong. Now, as we say, if you're a NASA scientist, you still use Newtonian gravity to send probes up to Mars, because the actual tolerance that you need is large enough that, yes, if I did it with general relativity, I would get a tiny little correction. It doesn't matter for that application. It matters for GPS. You better be using general relativity. But for many applications, you know that the predictions of Newton's theory are close enough for all practical purposes. So again, this is where the attitude comes in. If you're just interested in practical applications, and you know that the errors of Newtonian mechanics are below the level that you care about, sure, you can use it. And you can, as you say, you can program a computer to do it. Or maybe it's a much easier calculation than a general relativistic calculation. The people, I mean, I myself and the people I work with are steadfastly impractical people. We just want to know what the accurate theory is, even if it's of no practical use at all. Even if for all practical purposes we could get along well without it, we're just curious, right? I mean, we're just kind of upset that the basic foundations aren't well laid, because they're not, and they need to be worked on, but not really because we're running into practical problems. In fact, as I'm sure the people listening to this podcast know, one thing that fundamental physics dearly needs is data, is empirical data. I mean, it's much easier to make progress when your present theory has made predictions that have just turned out to be wrong, because then you can look at how they were wrong, and that might give you a clue. In a way, we're suffering from the fact that present physics can account for the data so well. And so people are rather furiously looking for places where they might get data that is clearly not what's predicted, and then that would give them some idea about how to proceed. Without that, you really are left with things like just logical coherence and consistency and elegance and so on, which are much more difficult to argue from. And it takes a different set of tools to really be guided by those kinds of purely theoretical considerations rather than be guided by some clear set of data.
Right. Yeah, so I'm very attracted to philosophy, Tim. I know nothing about it. It's so scientists, engineers, technologists tend to think in a certain way, right? I mean, we have our processes. We sort of predict what we want to get to at the end of the process, and we sort of make up things in order to get there. But the why question, the why question is a bad question, right? So you talk about this. So as you teach students, let's go to education a little bit now. As you teach students, is the why question still entertained in classroom?
Oh, sure. I mean, I mean, nobody, certainly not in philosophy, it's almost all why questions, or fundamentally, what is it questions. I mean, maybe it would help for people who don't know to just say a word about what happened in the transition from Newtonian gravitational theory to general relativity. Because, as I've already mentioned, general relativity gave you small corrections to the predictions. But underlying that was an absolutely, completely massive change in the basic explanation, right? So the why or the how entirely changed, even though the predictions only changed, marginally in a way. Right. So Newton thinks, well, I have the sun and I have the earth, and somehow if there wasn't a force keeping the earth in orbit, it would just fly away from the sun, right? I mean, he says, all right, it's orbiting, and then given his fundamental laws, in order to orbit, there has to be a force that's keeping it from just drifting away as it would do. And so he comes up with this idea of the universal force of gravity that drops off.
But he couldn't explicate how it worked, right?
No, he couldn't. And he had guesses, but when he writes the Principia, he very, very deliberately keeps the guesses under wraps, because what he says is, I'm going to talk about what, and this comes back to having data. He says, I'm going to talk about what I can demonstrate from the phenomena, right, from observations. And when it comes to the main question, but what causes this force, right? He says, that's exactly where Newton says famously, hypothesis non fingo. I don't frame a hypothesis. I'm not going to make a guess. Not because he didn't have a guess. He did have guesses. He writes elsewhere about what he thinks gravity really must be caused by. But he said he couldn't prove that or motivate that out of the phenomena the way he could just that there is this force. So Newton concludes there's this universal force that both keeps the moon in orbit around the earth and keeps the earth in orbit around the sun and makes the apple fall and so on. When general relativity comes along, it basically says, nope, no force. There's no force there.
It's just geometry,
All of these phenomena we're going to explain by the curvature of space-time. Now, Newton would have no clue what that meant to say space-time is curved or what that has to do with anything. So to understand general relativity, you really have to take all of Newtonian physics and throw it away and open your mind and learn an entirely new fundamental account of what's going on. At the end of the day, again, you get relatively small corrections to the predictions. So the effort is not mostly to account for, to give you a better practical tool, the effort is this just seems to be the right explanation.
So let me take a quick detour into education, Tim. I didn't think we were going to go there, but so if my hypothesis is right, that we can teach computers to do, how to build buildings, bridges, machines,
Mm-hmm.
All the education stuff that we are doing in engineering today, is that useful? I mean, should we have physics 101 and 102 or whatever? I mean, do you really need to learn Newtonian mechanics anyway? I mean, it's computers are so good at it.
I mean, let me give you an analogy here. When I was, of course, when we were in elementary school, there was a lot of effort just learning how to do long division and how to do calculation.
Yeah.
And before even the big computers came along, handheld calculators came along, and you could say, well, why are we even teaching kids to divide by hand, right? Tell them just, pick up your phone, go to the calculator and plug it in, and the calculator will do a better job. So sure, there was a lot of kind of algorithmic rote activity that at a certain point people had to learn because people were the only systems who could implement it. Once you have computers to do that, it frees you up from my point of view, it frees you up to teach much more interesting things, to teach more abstract things, and more creative things in a way, and more mind-opening things than learning long division. I mean, learning long division is just learning an algorithm, and it's kind of boring, right? And if you have to do it by hand, it takes a long time, and I can't say it's even good for your character. So I think a lot of this is an opportunity for education. I would imagine that a lot of engineering and so on was for a long period of time more or less just calculation, and so it was people implementing an algorithm which they were doing by hand, and they had to do accurately, which takes a lot of effort for a human and is very easy for a computer. Clearly, people using computers to do that drudge work can have a much more interesting time. They can explore a lot more possible forms. For example, if you're an engineer or if you're an architect and you're not quite sure, what your reinforced concrete will hold up to, and you're interested in all the different forms, aesthetically the forms you might, but it's not clear that this thing is going to stand up. I mean, that's what happened to Frank Lloyd Wright when he started out. Was he was using reinforced concrete, and people said that won't even stand up, and he had to prove them practically, actually, by building.
Yeah.
Yes, it will. I would think that would actually make the job much more interesting because you have a larger space to explore with the aid of the computer. And it forces you to think more abstractly. It forces you to think in a much higher level way, the kind of thing a computer really can't do well.
Yeah, so let me sort of conclude. So some of the Scandinavian countries, like Norway, for instance, have moved away from, I mean, Norway has been a leader in education for a long time, moved away from this idea that, the education thing is sort of fixed. You take physics 101 and chemistry 102, that type of thing. And they're saying, okay, let the student sort of design his or her curriculum based on what he or she thinks is useful. I'm very attracted to that idea. I think in the US, we are so far away from it, right? I mean, what do you think?
Yeah, I certainly think that the idea of giving students a lot of freedom. I mean, it's ironic because when I was young in the 60s and early 70s, it was very much open classroom, kind of let the kids do what they want to do and find themselves. I mean, a little bit hippie.
In the US?
In the US, yeah, where I was, in the schools where I was, it was really the height of that, of getting away from very strict rote, sequential kind of things.
Yeah.
And very much let the child find their own way. And it was what I needed. It may be that other kids can't handle it so well, or it doesn't work out so well. You're treading on one little thing, which I'll just mention because it'll probably come up. I actually think the way physics is taught is a bit of a disaster, exactly because we start with Newtonian mechanics. We basically use Newtonian mechanics as a tool for introducing calculus and various other mathematical tools that we use. But
you're taught bias.
Do that. There are a bunch of Newtonian principles that students imbibe or absorb without even being aware of it when they start out. And it forms a very, very strong conceptual structure in terms of which they think about all of physics. And as I pointed out, the problem is Newtonian mechanics is wrong. And so they're kind of coming into it with a, in my opinion, a bad structure in their head. I mean, for what it's worth, you can't quite jump straight into quantum theory, but actually if you did electromagnetic theory, you could use that also to learn calculus and so on. It would actually, I think, be a better example of physics, a more productive one in the future. But there are so many years in which this curriculum has been formed and all the books are formed, I can't imagine it's really going to change. But you would at least hope that people would be aware that you're kind of doing something a little sneaky to kids, because you're starting them out telling them lies.
So let me ask you this, Tim. So
you take them back, right?
Sorry to interrupt. So let me ask you this. So when we sort of get kids into Newtonian mechanics, get the basic principles right, I grew up in India. It's a very systematized education. You learn X, and then you learn X prime, and then X double prime, type education. So when you do that, and then you say the whole science has changed. I mean, all the stuff that we have taught are incorrect, and the technology and the understanding has changed. And so now all the kids bring to the table sort of their intuition based on the previous education.
Right.
You say, I don't understand this thing. I mean, I have to have, so we had to talk about Bell's paper and others. So let's just talk a little bit about quantum mechanics. It's sort of what happened, right? I mean, so this, these guys come along and they say, the whole stuff is completely different. I mean, it doesn't work like that.
Right.
And then all the people who studied classical physics say, let me apply my intuition to it. And I don't understand it, Yeah, and they all get together at Copenhagen.
Yes, and then eventually you say, don't apply your intuition to it, and then don't have any intuitions about it, and then just shut up and calculate. I mean, you see the steps, right? I mean, intuition is a great thing because you need to have a kind of intuitive feel for what's going on, even before you get down to writing down the precise and solving the precise equations. This is the kind of thing that actually, like, Richard Feynman was really excellent at. And I mean, Feynman famously said, if you can't explain something to a freshman physics class, you don't understand it yourself.
Yeah. And
there are various things that he realized on thinking about it, he couldn't explain it to a freshman physics class, and that he really didn't understand it. So, I mean, intuition involves having a basic picture of what's going on. And then when it comes to applying that in detail, okay, you get down to the details, and that can get very sticky, but you at least have something to start with. As I say, students sort of, their basic intuitions are Newtonian, because that's the way they're taught. When they get to quantum mechanics, they're not replaced by anything. And I often tell the story that happened to me. My first quantum mechanics class when I was an undergraduate, the professor was going through a certain situation within a magnetic field, it doesn't matter, and how the things behaved. And I put up my hand and I said, well, can I think of it like this? And I gave a little model for, this is a magnet and this is blah, blah, blah. And his answer to me was, no, you can't think of it like that. But that was the end of the answer. It wasn't think of it like this. It was,
It is an
don't think of
alternative,
it, right? It was, here's a mathematical formalism. It'll make the right predictions. Don't try and have any intuitions. And that's just bad. That's an error, partially because nobody can do it. And so you have all these intuitions that kind of flood back in, or are lurking beneath the water that you never got rid of because you didn't. The right way to get rid of a bad intuition is to replace it with a good one. And so if they don't give you anything to replace it with, then you're just stuck, right?
Yeah. So let me ask you, so suppose we have kids playing billiards for a while,
Mm-hmm.
and then you say, you go play chess. They will bring no intuition
Right.
from billiards to chess, right? No, absolutely nothing. I mean, they will bring a lot of biases to chess. And they say, things should move this way and that way. But
Well,
none of that
I
is
mean,
useful. Yeah.
I mean, you have to be, well, they will, if they're really good billiards players. Again, this is a question of these levels of abstraction.
Yeah.
I'm not one, but I know enough about billiards to know one of the things a really good billiards player does is look beyond the particular shot they're making, right? So you say, okay, I want to put this ball in that corner, but then they think, yeah, but where do I want the cue ball to be afterwards, right? That's going to depend. Then that's going to determine the spin I put on it. What's it? And so you're thinking a few moves ahead, as it were.
Yeah.
That's a good thing if you're playing.
That's true. Yeah.
Right? Not just what am I going to do with this move, but what further consequences will there be? Where will that put me? Where will that put my opponent? So at a very high level, you learn skills. But I mean, sure, billiards is just about physical motion at the end of the day, and chess isn't. Chess is just about strategy. I mean, you can play chess in your head. I mean, good chess players don't even need a board. It's a series of abstract moves.
Yeah, but it's an important point, though, what you say. I haven't really thought about this. So even in billiards, it teaches you how to think ahead. And thinking ahead is a critical skill, in chess also.
Absolutely.
He's sort of imagining what's going to happen, right?
Yes.
And it's a transferable skill in some ways, right? I didn't think about it. Yeah.
And that's a skill of basic reasoning. I mean, to anticipate, if I do this, if I say this, then what's the next question? And what's the next answer? I mean, there's for some reason, there was this book, maybe you knew it, Zen and the Art of Motorcycle Maintenance, that I liked a lot when I was growing up. And there's a scene where the protagonist is in a class arguing with the professor, and the professor asks him a question, a very simple sounding question like, would you accept a nicely prepared meal, or something like that?
Yeah.
And in the story, the student just stops to think, and he thinks, well, if I say yes, then he's going to ask me this, and then he just ends up falling completely silent, playing out in his head the dialectic, right? How should I answer this question? Because then that will lead to that question, that'll lead to that question. So that's basic logic, right? That's understanding that when you make an assertion, you're then responsible for all of these consequences, even ones you haven't thought of. And then you try and think ahead. And that's a really important skill. I mean, that's the basic skill of reasoning.
Yeah. So then comes quantum mechanics.
Right.
And all hell breaks loose
Right.
in many ways, right? I mean, it is not very intuitive. I mean, I don't know much about it, but it appears to create problems for humans from African savannah. We had some expectations how things work. And then this guy Bohr comes up with some stuff that most people can't understand. So then that is when things have, even Einstein couldn't understand. I mean,
Well,
it's a
Einstein
lack of
was very upset
intelligence. Yeah,
about the theory for that
yeah,
reason. Yes, he always complained about. I mean, Einstein sort of actually. I mean, Planck kind of started the theory. Really, it started in 1905. Einstein, between inventing special relativity and proving the existence of atoms, actually founded quantum mechanics, looking at the photoelectric effect. But Einstein was always very upset
Hmm.
that there were rules, but no explanations. I
Yeah.
mean, the quantum mechanics involves at its center this thing called a wave function that you assign to a system, which doesn't really have any good classical analog. Okay, fine. You write it down and you have an equation for how it evolves. All of that's kind of okay. But then how does that connect up with what I can predict? And eventually there's a thing called Born's rule where they said, well, take this function, which is a complex function. It's got I in it, square it. Okay, I know how to do that. That's just math.
Yeah.
And now treat what you get as probabilities. And you're going, well, where did probabilities come from? I mean, there's
Yeah.
no, why am I now talking about probabilities? And the answer is because that's what Born rule says to do. I mean, there's no explanation offered at all for why you're suddenly talking about probabilities. Um, and Einstein just thought that was completely unacceptable. It's not that he was, people often say he was upset because it wasn't a deterministic theory, but it's clear from his letters
Yeah.
that wasn't it. It wasn't because it was non-deterministic. He could accept that if he had to, but
Yeah.
it was just because there was no explanation going on. There was
Yeah.
just this kind of abstract set of calculative rules and no underlying physical picture at all.
Hmm.
Now, Bohr, in one way, seemed to be saying, well, that's because there is no underlying picture, and you're upset just because you won't give up your desire for a classical picture, and now is the time to give it up. But Einstein correctly saw that Bohr didn't have any argument for that. He didn't have any reason to think you couldn't have a much more explanatory, clear account. He just kept insisting you shouldn't want one, and Einstein never accepted it. And Einstein was right. I mean, here. So
Yeah.
could you give people? I mean, it's hard to say because there isn't a single theory, quantum theory, because there's just this mathematical formalism and then different attempts to understand what the physical basis of it is. But
Yeah.
if you have a clear theory that does give you an exact physical basis, you can develop intuitions about it. There's no question. But
Yeah.
you just have to know what it says, right? You can't develop intuitions about just a set of rules.
Yeah. Yeah. So I was thinking, Tim, probabilities are not a big problem for humans. We've been thinking about them for 10,000 years. If I go to this water hole, what's the probability of finding a line there or, something like that, right? So probabilities is something that we internalize. The problem is we have some expectation of determinism in some ways on physical systems. And you say it cannot be probabilistic. That's where the intuition, 10,000 years of
Right.
intuition fails, right?
Well, that's a bit. I understand what you're saying. It's a bit hard. I
Yeah.
mean, you think a very standard physical system that people thought a heck of a lot about is a pair of dice because they were
Hmm.
gambling on it, right?
True. Yeah. Yeah.
And it's not a fancy system, right? You just have these cubical items and you're throwing them on a felt table. Of course, it's very important that at a practical level you can't predict what they're going to do.
Yeah.
Now, people generally thought, even though we couldn't predict it, there was the physics of how you threw it
Hmm.
exactly and where it hit the table exactly and how thick the felt was exactly ultimately determined the number that would come up.
So there's classical
But that
physics
was,
behind
but
it.
of
Yeah.
course, they had to think
Yeah.
probabilistically because none of that was available.
So that was the issue. There's a classical physics behind it. So we can sort of rewind time and think about how the dice rolled,
Hmm.
how was it thrown, how far up in the air was it thrown, and all that stuff.
Right.
The problem for intuition is then quantum mechanics sort of destroys everything in some ways
Well,
for humans. No?
again,
Yeah.
there are, again, there's not a single thing quantum mechanics. There are ways of understanding quantum mechanics which are deterministic, the so-called pilot wave theory.
Oh yeah,
It's a
yeah.
deterministic theory. And in that theory, when you say, but then why can't I predict what the system's going to do? The answer is just as with the dice, you don't have enough information. And there's kind of a deeper answer as to why you can't get enough information, because of course, acquiring information is itself a physical process. So the laws of physics can control how much information you can acquire about a system.
Okay.
But it is possible. It's not as if the phenomena tell you you can't have a deterministic theory. Actually, we know you can have a deterministic theory. Most physicists don't accept that theory. They prefer to have an indeterministic theory, and maybe it is indeterministic. I mean, you can't prove it one way or the other.
So why do you think most physicists don't want that? Because my intuition would be that physicists from
Right.
our regime would want a
Yes.
deterministic theory.
So there's a wonderful book by Jim Cushing called Quantum Mechanics: Historical Contingency in the Copenhagen Hegemony. That's the subtitle. And the historical contingency part, and many people have argued this, and I think it's true. The historical contingency part says, well, what if instead of starting with the Born rule that I just mentioned, which is this probabilistic thing, what if really this pilot wave theory, which was already suggested by de Broglie back in 1925, what if that had become the dominant way of understanding quantum mechanics? And then everybody would have said, yeah, it's really deterministic theory. And then if a few years later, Bohr or Born had come along and said, no, let's replace your deterministic theory with a probabilistic one, then people would have looked at him like he was crazy and said, why should we do that, right? We have a deterministic theory. It's giving us all the right predictions. And so this was Cushing's point, and many people have said this, that the particular set of choices that ended up being accepted by the physics community about quantum theory are not well grounded in argumentation. They're not well grounded in phenomenon. They just were what Bohr just happened to be a very magnetic guy, apparently. Apparently he had this
He's
amazing
a salesman.
personality.
He's a salesman, yeah.
Yeah. And I mean, there are interesting letters at the time. De Broglie himself writes a nice letter at one time, and he says, well, the difference was that Bohr liked to organize. He wanted to be a leader of a movement. And I didn't want to be, and Einstein didn't want to be, and Schrodinger didn't want to be. So we all just went off on our own and each did our own thing. And we didn't form a group, right? Politically, it was just the individuals. And somehow Bohr was a big organizer of people. And he managed to create a kind of coherent group. They actually disagreed with each other more than you might imagine, but they presented a unified front to the world, and they managed to win the public relations battle. That's the situation. And it's a bit shocking because you'd expect that what's written in all the physics books would be a bit better grounded than that, but the fact is it isn't.
Yeah, so I think you talk about this, Tim. So there was sort of a bifurcation of people who love sort of mathematical descriptions of things and people who want a physical connection to mathematics. And Einstein has always been on the latter side, right? I mean, he imagines how things work in the physical world. And there were a group of people who said, I mean, it's all about mathematics. I mean, why do you need a connection to the physical world? Is that what happened?
Well, I mean, there are relatively few who would literally come out and say, why do you want a connection to the physical world? Okay, I mean, that's pretty blunt, and that would be a bit daring. It's certainly true that Einstein, I mean, he was not himself a great mathematician, and he used a lot of intuition. He thought about concrete physical situations and used concrete physical principles. And others were better mathematicians, and they would just be happy given some equations to derive a result. Um, Everybody kind of agrees that at some level these mathematical items have to be representing the physical world. But how much attention they're paying to how they do that is quite different. I mean, Ed Witten, who's very famous for developer of string theory, and people say, one of the greatest mathematicians of all time. He won the Fields Medal in mathematics. We had him up at the philosophy department at Rutgers to just talk about the foundations of physics and talk about Schrodinger's cat and the measurement problem, these sort of very basic problems. And he was game, and he came and talked and for about an hour and a half. And at the end, he said, I haven't thought about this stuff in 30 years. My job is to calculate wave functions, right? That's my job. And all this stuff about what they mean and so on, that's somebody else's job. And, you can take that attitude, especially if you're good at calculating. There's need for it. But to only take that attitude and not recognize the importance of the other part, namely, how does this mathematical structure represent the physical world? That's just to blind yourself to the interesting questions, it seems to me.
So I have a philosophical question for you, Tim. So what is physics for? When I was going through engineering school, I did, balls rolling down the, the inclined surface. I could compute stuff. I could build things. So suppose we come to a place that we can build buildings, bridges, and machines. That's what physics should stop in some ways, right? I mean, what is physics for? I mean, yeah.
Okay, that's a very engineering statement you just made. I actually I was originally going to be an architect, and I took courses in civil engineering as a freshman. And I found it deadly boring, and so I didn't go on with it. And
so did I. But it took me 10 years to do
that. My attitude was just the opposite, and that's, I guess, I mean, I did a joint degree in physics and philosophy, and Aristotle said, philosophy is born of wonder, thaumas, this feeling that you see the world and you're just astonished by it, and you're trying to understand it. That's what I'm interested in, is just understanding things. Now, of course, if you understand them, that has practical consequences. If you really understand something, you can probably manipulate it better. You can probably predict what it's going to do better. You can build bridges better. But you can go very far also without understanding. Medicine for a long time was like that. I mean, people didn't understand. Until even late in the 20th century, if you asked a doctor why aspirins make your headaches go away, they'd shrug their shoulders and say, I have no idea. I know it works, right? I know as a practical matter, it's effective. And I know
it's
that
an empirical science.
You can do even controlled experiments to verify that it's effective. But you can find out that something's effective and not have a clue how it actually works. And those are just two different attitudes, right? A doctor might say, I'm not that interested in how it works. I just want effective medicines for my patients. I can respect that. I'm just on the other side. It's like, I just want to understand how it works. I'm just curious, right? I'm just nosy.
That's a really good analogy. So I don't think doctors really understand. Well, this is a grand statement, so I have to be careful. The medications that they prescribe is a function of the patient and the information that they've been given from the pharmaceutical company.
Right.
And they're using intuition, they're using experience to sort of say, is this medicine matched with this patient? And often it works, I have to say. That's sort of a similar concept, right? I mean, it is it's the idea that practice. So let me. So I don't know if this is true, Tim. So let me pose something to you. Is practice more important than really understanding?
Well, so this is, I mean, and this is the kind of thing, again, go back to Aristotle. he makes a distinction between practical reason and theoretical reason. The aim of practical reason is to achieve a practical result. If you're a doctor, you just want to save your patients. And the aim of theoretical reason is to understand things. Now, when you ask which is more important, I mean, it's a funny question. Of course, neither side should dismiss the other.
Right.
And I certainly have all the respect in the world for doctors. And doctors, again, are in this situation. There's so many medicines. They obviously could not be doctors and also have to try and understand how each medicine works, right? So they just, in order to be effective, they have to be aware that there are a large array of medicines, be aware of more or less which ones interact with which, and what they should try with patients. If they get too interested in exactly how it works, they're going to become researchers and they're going to stop being doctors. Now, researchers are important too, right? It's like saying, who's more important, the researcher or the doctor? They're both important, and people should find the occupation that best suits their own sense of what they want to do.
So let's talk about John Bell. This is a topic you are very passionate about.
Yes.
So you wrote a paper in 2014. I didn't know the date actually. What Bell did, and as you mentioned, in 2022, a group of people got a Nobel Prize for sort of proving what Bell was theorizing very, very early. So you say here on the 50th anniversary of Bell's monumental 1964 paper, there is still widespread misunderstanding about exactly what Bell proved. This misunderstanding derives in turn from a failure to appreciate the earlier argument of Einstein, Podolsky, and Rosen, often called EPR paper. You say here, I retrace the history and logical structure of these arguments in order to clarify the proper conclusion, namely that any word that displays violations of Bell's inequality for experiments done far from one another must be non-local. So there's a lot of terms here. So I want to get some definitions. So what is Bell's inequality in a very broad sense?
Yeah. So, I mean, it's called Bell's inequality because it's literally just an equation that has an inequality sign in it. And what the equation is about is just observable statistics. So the idea is Alice, we always use Alice and Bob. Alice and Bob are in their laboratories very far apart from each other. Alice and Bob each have an apparatus that can be set in different ways. And we're going to send a pair of particles to them that have been prepared in a special way.
Entangled particles? Entangled particles.
Entangled particles, yes. They will be. This comes out of quantum mechanics and the theory of entanglement. But again, you don't have to know anything about that to just understand that that Alice and Bob can each choose the setting of their apparatus. They choose that setting, the particle comes in, and then the particle will react in one of two ways. You can think of it as, a dot up here or a dot down here on a screen, or a red light goes on or a green light goes on. So it usually just a binary response. And the statistics in Bell's inequality are just about correlations described in terms of what did Alice do, what did Bob do, what result did Alice get, what result did Bob get. And there are correlations, right? You notice, whenever Alice did this and got this result, and if Bob did this, then he got that result. I mean, things like that. Or whenever Alice did this and got this result, 75% of the time, if Bob did that, he got this result, and 25% of the time, he got that result. So these statistics are just empirically accessible. They're the kind of thing you can go into a lab and collect. And there's no theory much involved in collecting them, and you just have the data there. That was what the Nobel Prize was given for, was for increasingly sophisticated experiments of that sort. And what Bell...
So can I ask you, sorry, Tim, so can I ask you, so that the experiment, so we think about this far apart, under the galaxy or whatever, But the practical experiment that we are setting up clearly is not that far apart, right? So
Yeah,
so what's sort of the experimental setup
right. So
here?
by
Yeah.
far apart, what you really mean, what's important here is far enough apart that light cannot get from Alice's, as it were,
Yeah.
lab to Bob's lab in time to carry information about what Alice did or what result she got. Now, how far apart does that have to be? Well, it turns out you can do that within a single room if
Yeah.
you're really quick. You got to
Yeah.
be really quick and you got to be really clever.
Yeah.
You can do it.
Right.
It's easier if they're further apart. And Anton Zeilinger goes down to Tenerife, and there are these islands, and they set up situations where they have Alice and Bob are on different islands. So now they're kilometers apart, and you can go up
So
into space. They're going to do this. They can be hundreds of kilometers apart.
yeah.
It's far enough that light can't get from one side to the other in time.
Okay.
That's the
So
main.
these three guys who got the Nobel Prize in 2022,
Yeah.
guys and gals, um,
Well, they
the
happen to all be guys. And John
oh, they're all
Fowler,
guys. Okay.
Alain
Uh,
Spey, and Anton Zeilinger.
they sort of improve the precision and
Yeah.
measurement errors and all of that, right?
Yes,
Yeah.
yes. I mean, the very first experiments testing this inequality were done by Clauser. That was quite early. That was already in the 60s. Then Alain Spey exactly had very clever ways, because you want Alice and Bob, as it were, to be making their decisions very quickly about what they're going to measure. And he figured out a very clever way to do that with optical switches. And then Zeilinger kept stretching this further and apart and getting better and better detectors, higher and higher efficiencies, closing what are called loopholes that depend on the fact that some of your particles just go missing and they don't get into the data. So there were technical improvements,
Yeah.
but you knew what quantum mechanics predicted. Even Clauser was seeing what quantum mechanics predicted, even though there was a lot of noise and a lot of detector inefficiency. But what got through looked right. Aspey improves it, Zeilinger improves it to the point where everybody now says the loopholes are gone. We know that this is actually violated by nature. We know that Bell's inequality is violated by nature.
So Einstein is turning in his grave now.
Yeah, Einstein, it would have, I mean, I like to think it certainly came out exactly the opposite way Einstein would have expected. But I like to think he would have very deeply appreciated that. I mean, I don't think he would have complained about it. He would have said, well, nature's not the way I thought it was, and would have rethought a bunch of his positions. But, Einstein was right to stick to his guns as long as he did, because Bell hadn't proved his theorem and the experiments hadn't been done. I like to think that if that had happened, Einstein would have looked at it and said, well, I was wrong.
So can you define one more thing, Tim? So locality or non-locality has been a difficult issue for quantum mechanics against classical physics. So what exactly is locality?
So in the case of Bell's theorem, there's something that's sometimes called Bell locality or causal locality. And that basically just says, just as we say particles can't go faster than light, it just says causation can't go faster than light. It's really all it said. So if I push
information
a button
information
and that
exchange
button has an effect, that effect can't occur somewhere where light couldn't get there fast enough for it to happen. So that's the basic constraint that Bell lays down. Let's look at a theory that's causally local in that sense. And what he proves is that no matter what how you build the theory, try what you want, there are certain constraints in the data that locality will impose. Those are what the inequalities give you. If those inequalities are violated, then that tells you nature can't be local.
Right. So let me try to understand this, Tim. So there's this idea of statistical independence. And so basically, so if I understand this correctly, Tim, I don't have a background on this. So Bell is saying if two processes are completely independent, you expect an outcome. Probabilistic.
Let me say a word about statistical independence. So Bell Bell's theorem rests on two premises. One is this locality premise I just gave you about causation. There's another assumption he used, which is called statistical independence. Sorry, the dog's upset about something.
No worries, no worries.
And all that is, and he writes about this, is the same assumption we always make. So suppose I'm doing an experiment to test whether smoking causes, I want to know whether smoking really causes cancer.
Yeah.
And of course, the cigarette companies are fighting as hard as they can against this conclusion. And they say things like, well, no, smoking doesn't cause cancer. There's just a gene which both causes cancer and makes you want to smoke, right? So there's a correlation is not causation, as we say. And you say, well, okay, maybe. If you want to test that, you say, sorry, let me just let him see.
Oh, sure, yeah, absolutely.
You want to go out, buddy? Okay. If you want to test that in a clean way,
yeah,
the gold standard test is what's called a controlled randomized experiment.
Yeah.
So what do? You take a big set of mice and you randomly sort them into two groups, right? You flip a coin or whatever. And then you treat them the same in all respects except one. So you feed them the same thing, you put them in the same temperature. One you expose to smoke and the other you don't. And then you see, do you get a difference in the cancer rates? That's the gold standard experimental test for causation. Now, the statistical dependence.
Sorry to interrupt you. So we do that all the time in life sciences and economics.
That's right.
So I'm sort of puzzled by physicists saying, oh, no, that cannot be.
Yeah. So let me explain what the assumption is, and then you'll see how desperate they are, right?
Yeah.
So you say, well, if it turns out that the ones I submit to the smoke get a lot more cancer, that really shows that smoke causes cancer. And then someone says, no, because when you sorted them, you were flipping coins or whatever. Still, some were destined to get cancer, and they all got shoved over into the experimental group, and the ones not all got shoved over into the
biased selection process.
And you say, wait, you mean no matter how I did it, no matter what I did? They say, yeah. I'm just going to say that. And that's denying statistical independence. I mean, Bell's assumption is just that Alice and Bob can randomly choose their settings in whatever way they like, so that there wouldn't be any statistical correlation between how they set the device and the nature of the incoming particle. Of course, that's an assumption you make. It's an assumption we make in all experimental science. And some physicists are so upset about what he proved that they're willing to even say, I'm going to give up that. And it's just, I mean, you've gone off the deep end at that point, right? I mean, you just wonder, why are you so committed to locality that you're willing to essentially abandon all of experimental science?
Yeah.
You know, it's a very strange situation.
Yeah, so it sort of goes back to education we talked about. So classical physics and even general theory of relativity gives you some intuition that things are local.
Yeah.
And then out comes this sort of crazy thing that says, things are not local.
Right.
And you try to apply your intuition and it doesn't work. I mean, your brains are rather constrained in many ways. I mean, it's a function of all your experiences, all the stuff that you have done in the past. You're trying to map experience to the future. And you often fail. Yeah.
I think you're being a bit too kind there. I mean, these are the same physicists who happily, I mean, people all had this intuition forever that the world must be deterministic. I mean, Leibniz called this the principle of sufficient reason. If something happens, there must be a reason why it happened that way rather than some other way. And the physicists say, oh, we'll give that up, right? I mean, we'll just throw that out the window.
Yeah.
We're open-minded. And now you say, well, what about locality? No, I will never give up locality. So it can't be explained in a kind of rational way because they're behaving in an entirely inconsistent manner. Yeah. If you're open-minded, and you should be, you should say, yes, I have these very deeply held beliefs. I should consider they might be wrong. And I should, listen carefully to someone who's suggesting exactly how they might be wrong. But you should never be in a situation where you're so attached to one belief that you're willing to just jettison everything else to save it, right?
Right.
That's not a reasonable way to behave.
Yeah, so I'm a bit glib about this, Tim. So there are magicians in India
Yeah.
who uses the internet, and you say, you tell me what your problem is, and instantly I'm going to solve it by magic. And quantum mechanics, in some ways, looks like magic to most sort of conventionally thinking people, right? That was the problem.
Well, I mean, we say that, of course, when I was a kid, remote controls on TVs look like magic. I mean, here I am sitting in the bed and I have a little box in my hand and I press a button and the channel changes. Now, once you understand, okay, there was a infrared light coming out of this little box and received by the TV, and you say, okay, it's not really magic. So.
But there's a velocity of
the
light
question
problem
is,
here.
can you demonstrate in a rigorously controlled environment that it really works that way? That's what magicians can't do. I mean, that's what, if you know the great Randi, the amazing Randi, James Randi, was a magician, and he spent most of his life debunking a lot of parapsychological and paranormal claims, but he debunked them by saying, well, if you can do that, come in here and I'm going to set up the situation and show me you can do this. Yeah. And he would just put certain guardrails in place so you couldn't cheat, and then when they couldn't cheat, they couldn't do it. I mean, that's the way I think you should deal with magicians is I mean, in fact, anybody who calls themselves a magician, the first thing you should realize is they are trained in deceiving you. That's all magic is. Magic is taking advantage of the weaknesses of the human mind to deceive you.
So let's talk about this entanglement and entangled particles one more time. So you get two particles, fundamental particles entangled. You send one to Alpha Centauri and one here. And whatever I'm going to do to my particle, you get an opposite effect over there. And there's no information, as far as we know, travel.
Well, there's no, and this is a very subtle distinction.
Yeah.
There has to, in some sense, be information that's transmitted from one to the other. It's not done in a way that necessarily we can use to signal. Right? So there's a difference between information transmission and signal. Signaling means the signaler has free control over something, and the receiver can observe something, and then there's a correlation. So what the observer can see gives information about what the sender did. That doesn't seem to be necessary, but there is information must be sent. I mean, that's the whole point of Bell's inequality. If no information was sent at all, then you just couldn't get these results.
Yeah, so I didn't quite understand this. So suppose we have another dimension. I know nothing about this, so I'm in a totally speculative world here. So suppose we have another dimension, just one dimension, not two, just one, and we have sort of a linear string attached to the two particles in that dimension that we cannot really see. But they're very, very close together. So there's no velocity of light constraint problem here. Is something like that might be happening?
Well, I mean, it's the last part that's the issue. Is that's why we don't put Alice and Bob right next to each other. If Alice and Bob were really right next to each other, then you could explain all this without any problem. Right. Now, there's some people who have kind of suggested in a speculative way, well, maybe the particles, even though one's, as it were, in a lab on this island and the other is in a lab on this other island, and they're 100 kilometers apart, maybe in some extra spatial dimension they're really still close to each other, right? That is a kind of, all right, it's a speculation. It has nothing to back it up, and it doesn't really account for what we see. And we have no physics that would suggest that. But that's the kind of thing people try to say to get out of this. I mean, The fact is, even though in any normal sense, I've separated these two labs by hundreds of kilometers, and they're going to do this up in space, and then you can really go far apart.
Yeah.
By any normal meaning of the term, these are really far apart.
Yeah. Yeah. So as you assert, there is information exchange. So I remember, was it, the two pairs of socks? Einstein's early intuition was that I said, send a blue sock over there, and I keep the red sock, and there's nothing really interesting about this problem.
There's nothing interesting about that. Of course, it's not merely that events in different places can be correlated. Of course, they can be correlated, and Einstein was perfectly aware of that. He said nothing mysterious about that. What becomes mysterious? You really have to get into the very precise mathematical correlations that Bell discovered.
Yeah. Let's talk about that. Yeah.
And so when Einstein, Podolsky, and Rosen write their paper in 1935, they notice some correlations that are predicted by quantum mechanics, but those correlations do not require non-locality. They're easy, simple, local theories that would account for those correlations. Those don't violate Bell's inequality.
Okay.
What Bell discovered is that there's a wider set of correlations, and when you look at all of them, you find ones that can't be explained in the way Einstein wanted to explain things.
So, without understanding anything about this, Tim, so from an engineering perspective, so there is a expected correlation. Correct me if I'm wrong. So let's say I have two statistically independent random processes, and I have an expected correlation between, totally random, but I still have an expected correlation between these two processes. So I can put an upper limit on a correlation that without information exchange cannot be violated. Is that the way to think about it?
So this isn't quite right, but let me give you, I've used this example just so the listeners will understand the sort of thing we're talking about. So imagine somebody's playing a game with you, and it's like a kind of 3-card Monte. They've got 3 cups, okay? And they're going to prepare the cups in whatever way they want. And you can then go and freely choose any 2 of the cups, right, to look under. And what happens is that when you lift a cup, you either see a red ball or a blue ball, okay? And it turns out that every time you do this, you see 1 red ball and 1 blue ball. And you start to say, but wait a minute, I don't understand. If you can't have put all red balls or all blue balls under the cups, because then I'd always see the same thing. But if you mix colors, you have to use 1 red and 2 blues, or 1 blue and 2 reds. I should sometimes pick up 2 that are the same color, right? But no, every time you do it, they're different colors. Now, that's a clear statement of a correlation, right? That's just statistics.
Okay.
And if you look at that, you say, well, I can't explain those statistics if you're not cheating, right? I mean, one thing you can't be doing is not cheating. You can't just be putting these balls under the cups and then I'm lifting them and I always get opposite colors, because no matter what you did, there would have to be a way in which I could pick 2 that would be the same color. It's like that.
Are we sure our ex-president is not involved in this scheme?
I'm sorry, what?
Are we sure our ex-president is not involved in the scheme? If he's involved, I know.
Well, you have to be very clever. But it turns out even if you want to cheat, in this case, the cheating would have to be very clever, right? Because somehow, in the game I just gave you, somehow the person would have to wait until you choose the 2 cups, and then somehow manipulate after that point and before you pick them up to make sure they were different colors. That's the kind of reason why then you say, well, wait, why don't I move these cups further and further apart until, as it were, Alice is doing, I mean, that's more or less the idea, is that there's certain phenomena that you just say, if everything was on the up and up, and there was no causation going on underneath behind the scenes, you just couldn't see these statistics.
Right. So So let's go back to the foundations again, and I want you to talk a little bit about what you're doing in Croatia and the John Bell Institute,
Yeah,
if that's right. So at the end of the day, I mean, we see a lot of things. We have a lot of observations, we have a lot of data. We have different theories. Unfortunately, it would have been nicer to have just one theory. But they don't fit. So there
right.
is something foundational that we haven't figured out, right? Is that the idea?
That's right. I mean, there's several things to say. One is just forget everything else and focus on quantum theory. There we have a mathematical formalism and no agreement as to what it means,
Yeah.
what it's telling us. So there are different approaches, and then some people who are interested in this are exploring them and trying to develop them and make them clearer and so on. Then there's this big problem that quantum theory of every form seems to be in conflict with relativity.
Hmm.
And somehow we need to put those two together. That's generally called the problem of quantum gravity. Every physicist understands that hasn't been done. Nobody's clear how to do it. And again, these are very foundational questions in the sense that if you solve that problem and put quantum theory and relativity together somehow coherently, I don't think it's going to make a difference to technology. I don't think it's going to, we're going to build better bridges or anything. We'll just be able to understand things better. I mean,
It's
that's,
just knowledge.
yeah,
Just
it's just
knowledge. Yeah.
knowledge. And so this kind of, these kinds of questions are questions in the foundations of physics. They're questions that largely are not, physicists are not taught to ask or answer, so they're a bit in the dark. I mean, they're taught well to calculate, but here you can't calculate your way out of this. And so some people who were trained in physics found they couldn't pursue these questions in physics departments. Then they moved to, say, philosophy departments. There turned out to be more mathematical physicists interested in this, people in math departments who are mathematical physicists than physicists. Anyway, the point of the John Bell Institute is just to create a place for all of these people who tend to be distributed in different departments and distributed all over the world geographically,
Yeah.
to have a home, right? I mean, we have a kind of a theoretical home. I'm hoping to create a physical home in Croatia, probably an actual physical location where in the summers people interested in this, students interested in this, could come for various sorts of summer schools or workshops to work on these sorts of issues.
It's an important initiative. So you see, you have some sort of GoFundMe thing going on,
Yes.
or yeah.
I mean,
So,
I found a location. I mean, 5 years ago when I got this idea, I found a location which I really liked. I put money into building a lecture hall there, and a room for serving meals and so on. And we ran summer schools there the first year, which was 2019. Then 2020 came and COVID came, and everything got shut down. The last couple of years we started doing things again, but now, and I set up the GoFundMe at the end of last summer, thinking I would be trying to purchase this location. It's turned out there are various legal issues. I don't want to, about who owns the road, this and that. I mean, just weird things that the banks are not happy about. So it's not clear. So I set up the GoFundMe. It's not clear we will be able to purchase the place I had in mind. I'm in discussions with the University of Split and maybe with the University of Zagreb about finding alternative locations to do that. And I mean, I happen to like Croatia. If we find a place outside of Croatia, we might go there. So right now, whatever we do, there will be costs. We need to try to recover everything we can out of the location we set up, and so on. But it's not, at this moment, it's not clear to me what the way forward will be. I hope by the end of the summer to have a much better idea about what the concrete opportunities are. I think it seems like there are several different ways we might end up going.
Yeah. No, I mean, it's such an important initiative. I mean, there are a lot of things that we still need to sort of figure out. So I want to amuse you, Tim, with so we had classical finance for a long time.
Mm-hmm.
Around 1990, we had sort of like quantum mechanics. It's called real options. I don't know if you looked into this. So in classical finance, what we do is purely deterministic. So we say, I'm going to build this factory. It's going to take $100. So minus 100 year one. And then I'm going to make some widgets, and I'm going to make, $20 year two, $30 year three. And then I'm going to expand the factory in year four. There's another $100 negative. I put all this into an Excel spreadsheet. And then I say, there's a risk to it. So I have to divide that with a risk factor.
Mhm.
And out comes something called net present value, very much like, F is equal to M multiplied by A type thing. And
Mhm.
that's 99.99% of corporate finance, even today. Around 1990s, a group of academics, I was in academics, so I sort of tagged on with these guys, said, so Northwestern, Harvard folks, they said, so when you expand that factory, that's we call it an option. You don't necessarily have to expand
Right.
it. So in 2, 3, 4 years, the sales are good, you might expand it. Otherwise, you will just not do it.
Right.
So it's an option. So when you introduce that, it's sort of combination of what we call flexibility and uncertainty.
Mhm.
So stochastic uncertainty. So we have to sort of have stochastic simulation of uncertainty going
Right.
forward. And then we have to have dynamic programming to sort of look at the optimum decision at this point. It never went anywhere. No university offers these courses yet. After 25 years, well, 35 years. So it was sort of away from conventional ideas of determinism. It's sort of close parallel to classical physics, I think. Yeah.
I mean, let me just say, I mean, again, I don't know about economics. I certainly know in classical, what we call decision theory,
Yeah.
what you're calling the deterministic situation is considered trivial, right? I
Yeah.
mean, that is, if you're saying, I have a set of options. If I do this, this will happen. If I do that, that will happen. If I do that, that will happen. Then it's easy.
Right.
You say, which of those three do I want to have happen?
Right.
The hard problem of decision making is always decision making under uncertainty. You're not
Yeah.
sure what the outcome will be. You're not
Right.
sure, and then it ramifies. You get this whole tree of possibilities, and you need to somehow quantify the likelihoods
Right.
of various outcomes. And then usually you would calculate an expected value or something like that. Whether that's a
Yeah.
good idea or not is a different
Right.
question. But certainly there was a lot of probability built in. Now, none of that is quantum mechanics. That's just regular old classical uncertainty. Um,
Yes. Yes.
I'm a little surprised because all you described sounds like doing your financial planning, being perfectly aware that you don't know exactly what's going to happen, and trying to game out all the different possibilities, the way we talked about gaming out a game of billiards or whatever.
Yes.
I would expect any good financial planner would think, okay, there are a lot of ways this could work out. Let's think what our options are if, in year two, our sales are so low. Are we all going to go under? Can we do something else? That just sounds
So
like good sense to me. I mean, I'm not
yeah.
sure why anybody wouldn't be interested in doing that.
So there are two things there. One is we do a lot of simulations. We sort of understand uncertainty, but when you combine options or flexible decisions into the future, that's
Hmm.
a much more complex problem that you
Yeah,
can solve
sure.
on Excel.
Sure. You're going to get
Um, yeah,
combinatorial explosion.
yeah,
I mean, as soon
right,
as you have a lot of outcomes and a lot of options, then just the combinatorics is going to become
yeah.
very complex, right? So many
So
things happen.
yeah, so the analogy is, so 99.99% of corporate finance is like this today, which is like a lot of classical physics. And you say it doesn't quite work. Newtonian physics doesn't quite work.
Right.
But we send people to universities every year. Every MBA class at NYU and Columbia and elsewhere, it's just teaching this. You say, you put numbers into a spreadsheet, you divide it, and then you get a net present value and make a decision on that. And it is quite puzzling why we are here in many ways.
Yeah. Again, I don't know anything about this.
Yeah.
The sociology of it sounds like the sorts of things that happen in physics where you can't really tell a rational story about why people are sticking to what they're sticking to, except inertia.
Probability is, as you say, it's a very uncomfortable feeling, right? I would rather have a deterministic outcome. I mean, somebody tells me there's a 30% chance this will happen and 70% that will happen. That seems very, very uncomfortable for humans.
You better get you better get used to that being uncomfortable if you're going to go into finance, I would think, because that's the world you're going to live in.
Excellent. So, cool. Anything else you want to conclude on?
No, I think we've dabbled in a lot of different topics, and hopefully people will find some threads that run through this.
Yeah, I mean, education is I'm really interested in, how do we figure out how to teach the next generation of students?
Yeah.
And it's a regime change in many ways, in physics and finance and economics. And we cannot keep going back to what we did in 1950s and say, that is the way to start. If you start there, you're going to create people who have a set of biases that they will have a great difficulty transitioning. Yeah.
Right. And that you certainly, again, that's, I mean, in an ideal world, AI is going to take over the rote, boring tasks, and then you need to teach people. You don't have to spend so much time teaching them how to implement algorithms, and you can spend more time teaching them how to be creative and how to think, in different ways and approach problems from different angles. Unfortunately, as people say, it looks like it's going to be the opposite. AI is going to do all the painting, write all the novels, and then people are going to end up, doing these horrible jobs. But yeah, there doesn't seem to be a lot of applied intelligence in how the world works these days, if there ever was.
Yeah, I know that you have to go. So it just teaching people how to think.
Yeah.
But then there is also this question of policy, which is, so how do we do this? So maybe we'll have some sort of, minimum guaranteed wages or something like that. Because we don't need nuts and bolts, businesses anymore. I mean, we need those businesses, but the robots are going to do that, right? So it's a big transition that we're going through.
I mean, I think there's a huge, the biggest mental transition, which hasn't occurred yet, is the realization that we don't produce the life we have, right? We are living off the accumulated knowledge and effort of generations and generations and generations of people who came before us. And that's why we have such a better life than even, a hardworking medieval peasant who's putting a lot of effort in, right? Why are we better than them? Are we smarter? No, we're living off of all of the technology, all of the improvements, all the science, all of the political innovations of generations that came before us. And we're all inheritors of it. And we should stop trying to everybody grab what they can for themselves and think we're in a situation where if we deal intelligently, we can have a good life for everyone.
Yeah.
And we just have to stop being greedy about it, right? And thinking that it's a zero-sum game, and if I win, somebody else has to lose, because that's just not the way the world is. But we haven't made that transition. If we make that transition, we could imagine a world where everybody has quite a decent, people have healthcare, people have a decent standard of living, and can have enjoyable occupations, and everybody can have.
Yeah. Excellent, Tim. Yeah, thanks so much for spending time with me this late in
Okay.
Croatia. Really enjoyed it.
Thanks for having me.
Thank you.